I will start in like 5, 6 minutes. I'll just wait a few more minutes to see if anyone else is joining and then I'll start. Okay, I'll share my slides now. Right, I hope my slides are visible and that I'm audible. So, how this class will work is that basically, excuse just one second, I think someone wants to join. Yeah, so basically, for the first 1 hour or 1.5 hours, I will go through a summary of what Sir has discussed in the first week. So you guys might have watched the YouTube videos of week 1. So I'll summarize whatever was discussed in the videos, and you can clear all your doubts. And for the last half an hour or so, I'll discuss some sample questions. For since this is just week 1, uh, this time I'll be discussing the sample questions of assignment 0, which, as you know, was a practice assignment. But in the following weeks you can ask your doubts, and like if you have any particular question that you want to be solved in class, I'll give you my mail ID and you can send me the questions at that mail, and I'll solve those questions also in class. So I'll start the first class. Any time in between, you can stop me with your doubts. So I'll start. So firstly, I'll cover what Sir had discussed in his first lecture. So what he had talked about is that you have a nucleus, and in the nucleus, there is a spin. So the nucleus spins about an axis, and due to this spin, there is an angular momentum that is generated. And the angular momentum is a vector quantity, meaning it has a magnitude and it has a direction. This angular momentum is characterized by a quantum number called I, which is known as the angular momentum quantum number. And to find the magnitude of this vector, the formula is h bar root of I into I plus 1, where h bar is basically h by 2 pi, where h is your Planck's constant. So different nuclei have different values of this angular momentum quantum number, or I. The most common nuclei used in NMR spectroscopy, that is 1H and 13C, all have I values of half. So how do you, so this is a very classical way of depicting I. You can imagine in the nucleus as a sphere rotating around an axis or spinning around the axis. So that is the classical way of representing I. But I can have certain specific values, that is, it is quantized. So uh, as I said, if a nucleus has the angular momentum quantum number I, then it will have magnetic quantum number m ranging from I to minus I. So if the I is half, the m will be minus half and half, which you can see in this figure here. So here I has been written as L. So you can represent it by L also. So this is either I or L. And what happens is that this arrow that you can see, this is the angular momentum. So it's represented by an arrow because it's a vector quantity. The magnitude of this arrow is represented by this formula, So you can see here the value of I is half. So if you do half into half plus 1, that is half. So this formula, the portion inside the square root will become half into half plus 1 is 3 by 2. So it will become square root of 3 by 4. And that is what you have here, h bar square root of 3 by 4. That is the magnitude of this vector. And it is same no matter what. So here you can see for I half, you have the values of m as minus half and plus half. So minus half is going down and plus half is going up. And it is giving rise to two energy states having two different values of energy. So we'll come to that. But for now, it is enough to remember that the magnitude of this angular momentum, you just put it in the value of I half in this formula and get it as h bar root 3 by 4. So similarly, if you have I or L as 1, then again the m values will range from minus I to plus I. So you will have m values minus 1, 0 and plus 1. So you can see m minus 1, m0 and m plus 1. So again, they are oriented like this. So the 0m basically brings it to the transverse plane. So you can see the z-axis has been written here. And the z component of angular momentum is which is represented by Iz, has a magnitude of m h bar. So when your m is 0, the z component is 0. So the vector at that time, m0, is only in the xy plane because your z component is 0. And the magnitude, again, if you put I equal to 1 in this formula, it will become root of 1 into 2, that is root 2. So root 2 h bar, that is your magnitude of this vector. So m is only determining the direction, but the magnitude is constant for all three because magnitude depends only on the value of I, which is common. So what is this direction? This direction is represented by an angle, which is here theta, which is the angle that the vector makes with the z-axis. So you know cos theta is base by hypotenuse. So it is basically, if you can, this is a right angle triangle. So cos theta will be this z component divided by the vector magnitude. So z component we already know is m h bar, and the vector magnitude is this. So in the denominator you have h bar root of I plus 1, and then the two h bars cancel out, and you have cos theta given as m divided by root of I into I plus 1. From this, you can find theta by doing cos inverse, and that will give you the direction of the angular momentum vector. So you can find both the magnitude and the direction. So one thing is clear is that for a angular momentum quantum number I, the magnetic quantum number values range from I to minus I with integral increments of 1. So there are total 2I plus 1 values, because suppose I is 2. So it will go from minus 2, minus 1, 0, 1 and 2. So I is 2. So 2 into 2 plus 1. Total there are 5 possible m values. So there are 5 orientations of the vector possible. So this 2I, it is said to be quantized into 2I plus 1 states. So this is how the spinning motion of the nucleus translates into different angular momentum vectors having the same magnitude but different directions. And the direction is denoted by this angle theta. So now again, we are coming back to the nucleus, where the nucleus is spinning, and due to this, there is a angular. So we just discussed that due to the spinning of the nucleus, there is an angular momentum. Now, from electromagnetics, you know that whenever there is a spinning charged particle, a magnetic field will be generated. So each nucleus behaves as a tiny magnet, uh, and so all these magnets will have a magnetic moment. So imagine a crystal or a compound where there are many atoms, and each atom has a nucleus, and each nucleus has a different magnetic moment. Now, when there is no external magnetic field applied, so B0 is 0. Then all the small, so we are imagining the nucleus as a tiny magnet. So when the external magnetic field is 0, all these tiny magnets are just randomly oriented. So the net magnetic moment M is 0 because they cancel out. But suppose we apply an external magnetic field B0. So then there will be certain orientation of the magnets, which again I'll discuss in the coming slides. And then the net magnetic moments orient in such a way that there is a certain M value, which is the net magnetic moment, and M is no longer 0. This magnetic moment, represented by mu, is also a vector quantity because again it has a magnitude and it will have a direction. And it is represented by the product of gamma into I, where I is the angular momentum vector, which we just discussed, and gamma is a constant, which is called magnetoguidic ratio or guidomagnetic ratio, and it is a property of the nucleus. So you can see in this table here, there are many nuclei shown here. So some common nuclei used in NMR are 1H, 13C, 19F, 31P. So they can have the same value of I. You can see that 1H, 13C, 19F, 31P. All of them have I half. So you cannot distinguish them based on the value of the angular momentum quantum number. But the gyromagnetic ratio is very unique for each nucleus. And so how can you differentiate each nucleus is based on this gyromagnetic ratio. And depending on whether the gyromagnetic ratio is positive or negative, uh, the magnetic moment will be parallel or anti-parallel to I. So suppose gyromagnetic ratio is positive, then this product is positive, and so mu and I will have the same direction. But if gyromagnetic ratio is negative, which is a very rare case, but it happens in case of 15N. 15N has a gyromagnetic ratio that is negative. And in this case, the product will become negative, which means that the direction of mu and I become reversed. So this is another property of the nucleus, which is relevant for NMR. And how it is relevant, we'll come to that when we go to different practice problems. So what are the rules for this angular momentum quantum number? Is it that all nuclei will show NMR peaks, or are there certain nuclei which are NMR active and certain which are not NMR active? So there are certain rules for this. The first thing is that if the atomic number and mass number of a nucleus are both even, then the nucleus does not have a spin. So imagine this 12C6. 6 is your atomic number, 12 is your mass number, and both are even. In that case, the spins cancel out and the net spin of the nucleus is 0. If the net spin is 0, definitely the angular momentum is 0. So I is 0. And if I is 0, these NMR are called NMR inactive. They will not appear in the NMR spectrum. Now the second case is where your mass number is odd and your atomic number is even. So something like 13C6. Mass number 13 is odd and atomic number is 6, which is even. So in this case, you will have a half integer spin. That is, it will be multiple. It can be half, it can be 3 by 2, it can be 5 by 2. So basically, it will have an I value of n plus half, where n is an integer. N ranges from 0, 1, so on. So uh, another, just 1 second, I think again someone wants to. Right. So as I was saying, so if the mass number is odd and the atomic number is even, the I value will be n plus half, or it is called a half integer spin. And the third case is when the atomic number is odd and the mass number is even. So something like deuterium, that is hydrogen with the mass number 2 and atomic number 1. So mass numbered even, atomic numbered odd. In that case, the nucleus will have an integer spin. So it can have 1, 2, 3, and so on. In both case 2 and case 3, these are called NMR active nuclei. That is, they will show peak in the NMR spectra. So you can see here some more examples are given. So suppose we take 31P. In 31P, you have both as odd. Actually, this is a case where both are odd. So in this case also, uh, it is, so basically the only case where it's NMR inactive is where both are even. So like we already discussed 12 carbon, there is also 16 oxygen where both are even. So both I becomes 0 and your number of spin states, which is 2I plus 1, becomes 0. So this is the rule where you have NMR inactive and NMR active nuclei. So now we'll talk about how the different energy states are split in an NMR spectrum. So basically, we discussed that there can be 2I plus 1 spin states. And in the absence of an equivalent of an external magnetic field, these spin states have the same energy. However, when an external magnetic field is applied, the nuclear spin can be oriented either in the same direction as the, so suppose we have this arrow. If you see, this is the external applied magnetic field B0. When this is applied, the nuclear spin can orient itself either in the same direction as the external magnetic field or in the opposite direction as the external magnetic field. Uh, if it is in the same direction, the energy will be lower because the external magnet, it is following the external magnetic field. But if it is in the opposite direction, the energy is higher because it is going against the external field. Now, the energy of the state is defined by a dot product of two vectors, the magnetic moment vector mu and the external magnetic field vector B0. And a negative sign is also there. This mu, if we consider, conventionally, the external magnetic field is applied along the Z direction. So in all the images that you see, it will be shown along the Z direction. That is why I have written mu Z here. So mu, we have already seen the formula, is gamma I. Because we are calculating mu Z, it will be gamma IZ, and I can be written as m h bar, IZ specifically. So in the first slide, we saw that IZ can be written as m h bar. So mu Z can be written as gamma m h bar. So here we have a case where I is half. This is the case where I is half. So m values are minus half and plus half. These are your m values. So if you find this product, in this equation, you replace the value of mu with this gamma m h bar, and you replace m first with plus half and with minus half. Then you will get two values of energy, minus half gamma h bar b0 and plus half gamma h bar b0. In these cases, so when you have uh, clearly when the negative sign is there, because your gamma h bar and b0 are all positive, when you have the negative sign, that energy is lower, and with the positive sign, that energy is higher. And we call the lower state as alpha and the higher state as beta. So as you can see, when we have positive m values, the net energy is negative because of this minus sign. So positive m values are said to be aligned. And when we have negative m values, energy becomes positive again due to the minus sign, and that is said to be opposed. So this is how, in the presence of an external magnetic field B0, the energy state, so here you can see a single line is there. That means alpha and beta have the equal energy when the external magnetic field is zero. But in the presence of the external magnetic field, the two possible states, so here value of I was half, so 2I plus 1 is 2. So you have two possible states, and the two possible states here are splitting up in the presence of an external magnetic field into the alpha and beta states. So now, so you have a lower level and you have an upper level. So there are nuclei populating the lower level. So as we saw, lower level means it is aligned. So we will show the nuclei in the lower level with an upward spin and upper level with a downward spin. So that there are certain population in lower level and certain population in the upper level, and this is determined by the Boltzmann distribution equation. So if we consider n upper as the population in the upper level and n lower as the population in the lower level, this ratio is e to the power minus delta E by kT, where delta E is this energy difference. This is delta E, and the value of delta E, so you basically just subtract the upper minus lower, is gamma h bar b naught. So delta E, and it can also be written as h nu, because so when you have two energy levels, you can supply an electromagnetic radiation of energy h nu in order to promote a nucleus from the lower to the upper level. And also the nuclei from the upper level can relax to the lower level, and they will emit a radiation of energy h nu. So any electromagnetic radiation can be represented by the energy h nu, and so instead of delta E, we can replace it by h nu. And then if you put the values of the constants h and k, you will be able to calculate the difference in population between upper and lower levels. Now, one thing to note is that the population difference is actually very low. So suppose like here we have shown one where we have taken a general distribution. You can see that the lower level only has 9 additional nuclei compared to the upper level. It is because of these additional nuclei that we are seeing the NMR signal. So if h nu absorbed and h nu released is the same, then there is no net absorption. So you will not observe any signal. But because there is this additional 9 nuclei in the lower level, the absorption is greater. And so you will see an absorption spectra like this, which is basically your NMR spectra. So it is this difference in population between the upper and lower level that is dictating the NMR signal intensity. So now we have seen two things. So these arrows are your angular momentum vector I, and we have already discussed that the direction of I is represented by the angle that I forms with the z-axis. But there is another property of this angular momentum vector. So basically, so here only one arrow is shown, and if you draw a normal from the end of the vector to the xy plane, this is called a projection. So this line that is there, it's a projection. And where this line meets the xy plane, if you draw another line to the origin, then the angle that this forms with the y-axis or the x-axis is represented by phi, and it is called the phase of the spin. So this is the phase of the angular momentum vector. Now, in the absence of any external magnetic field, I can be oriented in any direction on the surface of the cone. So there is a cone you can see shown here, and on the surface of this cone, I can orient itself along any direction in a random manner. So for each of these arrows shown in this picture, there will be a different value of phi, that is a different value of phase. And because I is randomly distributed, the phase will also be randomly distributed in the absence of an external magnetic field. And this is called the hypothesis of random phases. But what happens when you give an external magnetic field? So as you can see here, an external magnetic field is given. And what happens is that, so this is your magnetization M. And this picture is again in the when you have not given an external magnetic field yet. So just ignore this B0. This is still in the absence of an external magnetic field. At that time, your entire magnetization is along the z-axis and any xy component is 0. So this is in the coming slide, we'll see what happens when you give a external magnetic field. But for now, it is enough to remember that in the absence of the external magnetic field, the equilibrium magnetization is fully along the z-axis. And why is that? So let us imagine there is a plane here, and I am going to, so each of these vectors will have x, y, and z components. So the xy components are all randomly distributed in different directions. And when you take the net of the xy components, they will all cancel out. So if you sum up the magnetization x plus y, this will come as 0. That is why the xy component is 0. But for z, what will happen? They will orient. So the lower cone, they will either orient in the upward direction or they will orient in the downward direction. But upward and downward is not equal. We have already seen when we were seeing the populations. So here you can see in the populations, the upper and lower, there is a small difference. And due to this, the net magnetization or the equilibrium magnetization is along the z direction. And that is what we often call as mz or m0. So I'll repeat this once again. Because the xy components can be oriented at any direction in this plane, if you take the summation, they will all cancel out. But for the z component, which can either come out to be in the upper or lower direction, there is a small difference in population. And because of this, there is a net Z component. And so the net magnetization in the absence of any external magnetic field is lying in the Z direction. So now imagine, this is just a classical comparison. So you have the Earth and you have so the Earth has a magnetic north and south pole. And if you have a compass, the north of the compass needle will point towards the magnetic south of the Earth, and south of the compass needle will point towards magnetic north of the Earth. If you force the compass needle to point at some other direction, it will again come back because it is getting attracted by the magnet in the Earth's core. So the compass needle is experiencing a torque due to the Earth's magnetic field. Just give me 1 second. Similarly is the case of the nucleus. So in the nucleus, so the nuclear spin, suppose it is initially directed only along this direction. But because of the external magnetic field, like the compass needle is experiencing a torque due to the Earth's magnetic field, the nuclear angular momentum is also the nuclear magnetic moment is also experiencing a force due to this magnetic field. And this is causing it to spin in this kind of, so this arrow that is here, this arrow will spin in this cone fashion. It will orient itself along different directions along the surface of the cone, and it will spin like that. And this is called Larmor precession. And the frequency of this spin, so whenever you have a spinning motion, you have a frequency. The frequency of this Larmor precession, that is denoted by omega 0, is represented by minus gamma H naught. H naught is basically B naught, that is the applied magnetic field. And gamma, as we have already seen, is the gyromagnetic ratio. So we have already discussed this before, that when I is half, you have M values of plus half and minus half. And there are two energy levels. And the energy difference between these two levels, which you will get by the subtracting the upper minus lower energies, is gamma H bar B naught. And we know that gamma H bar can be written as minus omega naught by this equation. So we can write the energy difference as minus omega naught H bar. One thing to remember is that when these arrows are spinning around in the Larmor frequency motion, the direction is always clockwise. So you can see the direction shown here is clockwise. And conventionally, it is the negative sign that indicates clockwise motion. So the negative sign here is indicative of the clockwise motion of the Larmor precession. Now I'll introduce another concept, which is basically the rotating frame of reference. So what is meant by that is that, just one second. So rotating frame of reference means that, so this is the angular momentum vector shown by this yellow arrow, and there is a cone, which is the Larmor precession, cone. Now, suppose your observer is sitting along this red circle that is shown here, and the red circle has the same frequency as this Larmor precession angular momentum vector. So the observer will think that there is no motion because the observer who is sitting in the red circle. So just 1 second, I'm having some connection problems. Right. So you can imagine that your observer is sitting along this red circle, and the observer is also moving, and the angular momentum vector is also precessing in a Larmor precession motion along this black circle. If both these motions have the same frequency, then to the observer there is no motion at all. So the observer will think that there is no B0 field because the observer is seeing that the angular momentum vector is not moving. So to the observer, the B0 field is 0. This is called the rotating frame of reference. And the use of this we'll come to later. Here I'm just introducing the concept. So the laboratory frame of reference is when the observer is standing far away. And when the observer is standing far away, he can see that the angular momentum vector is moving along in a cone-like fashion. And so he will think because the angular momentum vector is moving, there is a net magnetic field. But if the observer is also rotating at the same frequency, so suppose the frequency of the observer is omega obs, and this is the same as the Larmor frequency, which is the frequency at which the angular momentum vector is moving. Then to the observer, there is no motion of the angular momentum vector. So if the angular momentum vector does not move, the external magnetic field must be 0. And this is the case only in the rotating frame of reference. So I was talking about the lower and upper levels of energy, and the population of these two levels were represented by the Boltzmann distribution. Now we have seen that delta E in case of NMR spectroscopy, where I is half, is gamma h bar b naught. So instead of delta E, you can replace gamma h bar b naught and you will get the difference in population. So what this means is that if b naught is changed, the population difference also changes. So in order for this population to change, either from lower there will be transition to the upper level, or there will be, so transition can occur in either direction, upper or lower. So when there is a transition from lower to upper level, there is an absorption of energy. So where does this energy come from? And when there's a transition from upper to lower level, there is a release of energy. And so where does this energy go? This is where the concept of spin lattice relaxation comes. So basically what is lattice is, in crystal systems, so in crystals you have regular distribution of atoms, and that is called a lattice. Here we use the word lattice in a much more general format. Lattice represents everything other than the spin system under study. So suppose we are looking at a particular 1H proton. Any other carbon, nitrogen, even solvent molecule, anything connected to that 1H proton is considered as the lattice. So in this 1H proton system, suppose there is a transition from lower to upper level. The energy for this transition comes from the lattice. So in the lattice, there must be an opposite transition which releases an energy, h nu, which promotes the nucleus from lower to upper level. Similarly, if there is a transition from upper to lower level, this releases an energy h nu, and this must be absorbed by the lattice in order to undergo an opposite transition. So the lattice kind of acts like a sink. So any extra energy is dissipated in the lattice, or any additional energy required is also gained from the lattice. So when we change the magnetic field B0, because this upper by lower population ratio is changing, and this change is happening by this kind of transition, which is enabled by the presence of the lattice. So this process is called spin lattice relaxation or coupling, and it is responsible for population adjustments. So this spin lattice relaxation that we just talked about is characterized by a time constant called the spin lattice relaxation time T1, also known as longitudinal relaxation. Why longitudinal? Because it is also in the upward or downward. Sorry, just 1 second. Yeah. So the spin lattice relaxation time T1 is also known as longitudinal relaxation because the lattice is also the absorption or dissipation of energy in the lattice is also happening along the z direction. That is why it is called the longitudinal relaxation. Suppose, so we have two energy levels, alpha the lower level and beta the upper level. We are calling the populations as n alpha and n beta. The population difference at time t, if we represent that as n, that is n alpha minus n beta. And the population difference at equilibrium, if we represent that as n alpha 0 minus n beta 0. Then the equation is this, where n equal to n0 into 1 minus e to the power minus t by t1, where t1 is your spin lattice relaxation time. So longer the spin lattice relaxation time. So suppose, this value of t, if it is infinity, that means this term is going to 0. If t is infinity, this entire e term is going to 0. So n equal to n naught. So in order to reach equilibrium population, theoretically it takes infinite time. And using this equation, we can find the population difference at any time t. as long as we know the spin lattice relaxation time. Now, when is the NMR spectra observed? NMR spectra is, so again you have the two energy levels, plus half and minus half. It absorbs a radio frequency h nu from the lattice, and it gets promoted from the lower state to the upper state. And when it gets promoted, the spin also changes. So it was spin up and now it has become spin down. This kind of process is a quantized process because the absorbed energy must be exactly equal to the energy difference between these two levels, delta E. And so this absorption is a quantized process, and it is called as resonance absorption energy. This energy is in the radio frequency region, and the radio frequency region, so it is an electromagnetic wave, and so it can be represented by this kind of formula, which is 2h1 cos omega t, where h1 is the amplitude of the radio frequency and omega is the frequency of the wave. So if you imagine a wave, this amplitude of the wave is h1 and frequency of the wave is omega. So you have 2h1 cos omega t as your radio frequency. Now if we keep h1 outside, 2 cos omega t, we can write it as e to the power I omega t plus e to the power minus I omega t divided by 2. So as we discussed a few slides ago, positive sign means anti-clockwise direction and negative sign means clockwise direction. So e to the power I minus I omega t has the negative sign. So it is this direction which is clockwise. So we will only consider this component because we have already discussed that the Larmor precession happens along the clockwise direction. So if we have radio frequency of both clockwise and anti-clockwise direction, that particular radio frequency will affect the nucleus, which has the same direction as the Larmor frequency, which is the clockwise. So Larmor frequency is also clockwise. You can see this direction clockwise, and e to the power minus I omega t is also clockwise. So this is the one that we consider because it is the same direction as the nuclear spin. Now, in resonance, so we have the Larmor frequency we already saw is minus gamma h0. And when the Larmor frequency and the frequency of this radio wave, that is omega naught and omega, when they are equal, so you can we'll write the difference between omega naught and omega as omega r. Omega r is the frequency in the rotating frame of reference. So again, you imagine an observer. So you have this kind of frame and an observer is sitting in the frame and moving in the same direction as the Larmor frequency. In this rotating frame of reference, if your frequency of the observer and the frequency of the Larmor precession is same, then the net magnetic field observed by the observer is 0. So if omega naught minus omega is 0, that is omega naught and omega are equal, then HR is 0, where HR is the magnetic field in the rotating frame of reference. So so the spin seen by the observer is 0. So any magnetic field in the z direction is getting cancelled out because the observer is also rotating with a frequency omega, and the Larmor frequency is also precessing with a frequency omega naught. And when these two are equal, then the observer will think that the angular momentum is stationary. It is not rotating at all. So if the angular momentum is stationary, then in the z direction, there is no magnetic field. So the net magnetic field along z axis is 0. However, there is still a magnetic field in the xy plane. So initially, in the absence of B0, the entire magnetization was in the z axis. Now, when B0 is applied, the magnetization in the z axis slowly becomes 0, and the entire magnetization comes along the xy plane. So you can see the final magnetization is in the xy plane. Now it is not stationary in this plane, but it is also moving in a circular motion along the xy plane in a clockwise direction. So initially your entire magnetization M was in the Z direction. When a radio frequency or external magnetic field B0 is applied, the magnetization changes direction to come in the XY plane. And in the XY plane, it rotates similar to Larmor precession. So in the Z axis also, it was rotating kind of in a cone. In the XY plane also, it rotates similar to the Larmor precession. So, and eventually when you switch, so in NMR, what happens? You give the magnetic field for a short amount of time and then you switch it off. When you switch it off, again, this will come back to this direction. And that is why there is a decay of the signal. So here is basically shown like the way in which the NMR spectra is recorded. So your initial magnetization, yeah, this is actually like the decay process. So this is showing the decay. So initially, just ignore this initial and final. So initially it was in the Z direction. When B0 is applied, it comes along the X direction, XY plane actually. And in the XY plane, you have a detector, which here it is written as receiver coil. Now, when you, so this receiver is detecting the magnetic field and it is giving rise to the NMR signal. When you switch off the external magnetic field, again, it will go back to the condition that it was before, that is, it is in the Z direction. So again, I will repeat the process that happens is that initially the magnetization is only along Z. When B0 is applied, XY magnetization is created. But this XY magnetization, also known as transverse magnetization, is not an equilibrium situation. This will only persist as long as B0 is applied. The moment you switch off B0, again from XY magnetization, it will go back to Z magnetization. But in the XY plane, if you have a detector, so the detector is placed in the transverse plane or the XY plane, this will detect a signal and give rise to your NMR signal. So again, this is now, so this is all about the signal. Now, what about when B0 is switched off? So during B0, your magnetization is in the XY plane. As B0 is switched off, slowly the XY component becomes lesser and lesser. So you can see this red component or the XY component is slowly reducing and the Z component, which is the initial magnetization along Z axis, is slowly recovering. This kind of process by which the initial magnetization is recovered is called spin-spin relaxation or transverse relaxation. Transverse relaxation because the transverse component is reducing. And this is characterized by a time constant known as T2 or the spin-spin relaxation time. So how does this happen in practice? In practice, it is not like there is only the XY component is only in one direction. What happens is that initially, if you have the Z component pointing along the Z axis, and after your radio frequency is applied, the energy of the radio frequency forces the magnetization to turn by 90 degree and come in the XY plane. This is detected by the receiver or detector and gives rise to your NMR signal. Now B0, so B0 is basically the radio frequency that is supplied for this short time. After this short time is over, there is no additional energy. So what happens is that the vector that is along the XY plane starts reducing. And how it starts reducing is that it splits up into multiple vectors in different directions, and the net summation of these vectors has a lower magnitude. You can see initially the magnitude was much higher, but gradually the magnitude reduces till eventually in the XY plane, the magnitude completely becomes zero. And the only magnetization remaining is along the Z axis. So we discussed previously that when uh, we discussed the hypothesis of random phases. So I'll go back to that. The hypothesis of random phases happened when in the XY plane, the net magnetization was zero because it was cancelling out from the different directions. However, so because it was cancelling out from different directions, that is, the phases were completely random, the net magnetization along XY was zero. But when you apply a radio frequency, that is not the case. There is a certain transverse magnetization, that is XY component of magnetization. So the phase is no longer random. And that time, the system is said to have phase coherence. That means the system has a specific phase. But gradually, as the XY component reduces and the Z component goes back to normal, it reaches this situation where the magnetization along X and Y is again zero. So again, it reaches the case of random phase. So again, the phase becomes random. So initially, during the radio frequency, there was a phase coherence, but after the magnetization goes back to the Z axis, the phase again becomes random. That is why this spin-spin relaxation time or T2 is often is called a loss of the phase coherence. Because as the spin-spin relaxation is happening, that is, the system is going back to this situation, the phases are no longer coherent. They are becoming random again. So T2 is related with the loss of phase coherence. And what happens in this, your detector is in the XY plane. So as you go along this direction, your detector initially detects the highest signal because the entire magnetization is along XY. And as the XY magnetization reduces, the signal also decays to zero. And this is called the free induction decay or decay of the signal. Now, if you have an off resonance condition, so resonance condition we saw where omega was equal to omega naught. And if omega and omega naught are equal, the effective magnetic field in the rotating frame of reference, H effective, or we can call it HR, R because of rotating frame of reference, this was also 0. But in off resonance condition, where the omega naught and omega are not equal, at that time there is a certain effective magnetic field. And this effective magnetic field is represented by the vector addition of the z component and the xy component. So that is the case when it is not the resonance condition. Now, in an NMR instrument, normally what happens, you have this sample tube, you have the sample dissolved in the specific solvent, and the radio frequency coil, so you can see this coil around the sample. It is through these coils that the radio frequency energy is supplied to the sample. And once you supply the radio frequency energy, we discussed that the Z magnetization becomes XY magnetization. And XY magnetization is detected by the detector that is present in the XY field. So once the detector detects it, it converts it to an absorption spectra, which is what we see as the different peaks in the NMR spectra. Now we'll briefly look into the kinetics of this resonance absorption. So again, we are looking at I equal to half. And I equal to half in the presence of the B0 magnetic field. The nucleus has two energy levels, alpha and beta. Now, the rate equation. So basically, if you imagine a first order equation, alpha going to beta and beta going to alpha. So how would you write the rate equation for such an equation? So d n alpha dt, where n is the population of the alpha level, is minus p. So first we'll define a term p, that is the probability of transition. So it can either go from alpha to beta, or it can come from beta to alpha. And the probability of both these are equal, and this is P. So P is kind of like the rate constant of the reaction. So if you imagine a reaction like this, alpha going to beta and beta going to alpha, with a rate constant or probability of P, so we can easily write out the rate law. So d n alpha dt will be minus P n alpha, because the alpha population is reducing. So it is minus P n alpha, and depending on the beta concentration, it is plus P n beta. So it is just, so in a rate law, if we are, suppose we are doing the rate law here, alpha going to beta will go at a rate of minus P n alpha, and beta coming to alpha will happen at a rate of P n beta. So similarly, we can write the rate law for d n beta dt. So we will have these. So this is, you can just imagine it as a reversible reaction, reversible first order reaction having a rate constant of P. So then if you subtract dn alpha dt minus dn beta dt, it will be minus 2pn, where n is the population difference between alpha and beta. And this equation, if you integrate it, it will come out to give you n is n0 e to the power minus 2pt. So if t is 0, this entire term becomes 1 and n is n0. But if t is infinity, then if t is infinity, this entire term becomes 0. And so n becomes 0. That is, the population difference between alpha and beta becomes 0. So this case, this is an important case where t is infinity, the population difference between alpha and beta is 0. So both alpha and beta are equally populated. So if we have 2 nuclei in the alpha state, there will be 2 nuclei in the beta state. So there is no net absorption of energy, because suppose one nuclei is getting promoted, simultaneously one nuclei will come down. So there is no net absorption or release of energy. So there will be no NMR signal observed. This is called a saturated state. So if we plot this equation, if we plot n with respect to t, there is an exponential decay of n. So at t0, the difference between alpha and beta is maximum. But as the time is going to infinity, the population difference n is slowly decaying till it reaches 0. Similarly, this graph is very closely related to the graph of dE dt, which is basically the energy absorbed with respect to time. So if the population difference, so if the population, this is n is basically n alpha minus n beta. If population difference between the two states is maximum, energy absorbed will also be maximum. But as time goes, the two states are becoming, slowly they are becoming equally populated. And as they are becoming equally populated, there is no net energy absorption. And so the energy absorption curve is also decaying to 0. And when it goes to 0, we no longer see an NMR signal. So, however, in practice, what we see is that there is no case where this happens. This case, so this where the NMR signal is decaying to 0 does not happen in practical NMR. In NMR spectra that you record in the laboratory, the spectra does not suddenly become 0. The spectra persists. So why that is happening is spin lattice relaxation. So basically, even if you have a case where the lower and upper levels are equally populated, you have to remember spin lattice relaxation is a phenomenon that exists. And due to spin lattice relaxation, what happens is ultimately it will go back to the equilibrium phase. And what is the equilibrium phase? Where the population of the lower is greater than the population of the higher. Because of spin lattice relaxation, you always have a lattice, which is a sink for energy. So it will always relax back to the equilibrium state, and the extra energy released will be absorbed by the lattice. So because of the presence of the lattice, there is a mechanism for re-establishing the population difference. So this situation does not happen, and you always have a population difference, which is why the NMR signal does not decay with time. In order to include the effect of spin lattice relaxation, an additional term is included in the equation we derived in the previous slide. So we got this n equal to n0 e to the power minus 2pt. We have included an additional term minus n minus n0 by t1, where t1 is your spin lattice relaxation time. Now at equilibrium, We are representing the equilibrium population difference as N dash. At equilibrium means there is no change in the population. Equilibrium basically means all the properties of the system are constant and nothing is changing. So the population difference does not change with time at equilibrium. So if this is 0, this left hand side of the equation becomes 0. And if you solve for n, you will get that n dash, that is the population difference at equilibrium, is n0 divided by 1 plus 2p(t1). This is the equilibrium population difference. If n dash is not 0, that is we have a population difference, then we will see a NMR signal. The denominator of this equation, 1 plus 2p(t1), is called saturation factor. Why it's called the saturation factor is because if the denominator is very large, then what happens if the denominator is very large is that n dash tends to 0. That means the NMR signal would disappear, that is, it becomes saturated. That is why this denominator is called a saturation factor. So if the T1 is very large, so Sir was discussing in one of his videos in lecture 3, I think, that one person, he had recorded an NMR signal, but no signal was seen. And later it was found that it was because the spin lattice relaxation time was very large. If T1 is very large, the denominator is becoming very high. So n dash, that is the population difference at equilibrium, is becoming 0. And we have discussed that if the population difference becomes 0, no NMR signal will be seen. So that is the effect of the spin lattice relaxation on the NMR signal. Now, there are, just 1 second, I think someone wants to join. Now, there are certain selection rules to the NMR spectra. It is not like because there are 3 allowed energy levels that all possible transitions are allowed. Basically, the selection rule is that delta M can be plus minus 1. This is called single quantum transition. So from M1, it can go to M0 or 0 to 1. Or it can go 0 to minus 1 or minus 1 to 0. But it cannot go from plus 1 to minus 1 because then delta M becomes 2. So this is the selection rule of NMR, that only when the magnetic quantum number is changing by 1, those transitions are allowed. Now in NMR, we have seen that, so if you have 2 energy levels with a difference of delta E, and we can write delta E as h nu. So you would expect that only if there is a radio frequency of exactly delta E h nu, that this kind of transition will occur. So you would think the NMR signal will be very sharp like this, corresponding to a single frequency. But in reality, a broad signal is obtained. So the middle of this broad signal is your omega naught, but you actually observe omega naught plus minus delta omega. So you observe a certain line broadening. This happens due to 2 reasons. Firstly, according to the Heisenberg's uncertainty principle, delta E into delta T is approximately h bar, where delta E is the uncertainty in energy and delta T is the lifetime of the spin in that state. Because of this, there is always a finite value of delta E. So if the energy is uncertain, that means it is not only transition from one state to another state. There is a certain range of energy states both in the upper and lower level. because of the uncertainty in energy. And so there is not one single transition possible, there are multiple transitions possible, slightly varying in the frequency. And that is why we don't see this kind of sharp spectra. We see a slight spectral line broadening, this kind of spectrum. The second reason is basically called the field inhomogeneity. So if you have your sample tube and the magnet that is providing the external field H0 is not very good. So here it is providing, say, H1 field, but here in the sample it is providing H2 field. So different atoms in the sample, different nuclei in the sample are experiencing different values of the external magnetic field. When this happens, the absorption will also be at different frequency values. And so you can imagine different nuclei absorbing at different frequency values. So this will cause line broadening. So these are the two factors that affect the line width. Firstly, if there is a change in the lifetime in the state, that is the energy uncertainty. And secondly, it's the field inhomogeneity, where if the magnet providing the field is not good and it does not provide a homogeneous field, then this kind of line broadening can happen. Now there are certain equations that Sir discusses called the Bloch equation, but as Sir said, we don't have the derivations. You don't have to worry about the derivations of these equations. Um, and mostly the questions in NPTEL exams are of MCQ type. So if you can just remember the form of these equations, that is enough. So again, so here also I will not, I will just discuss the basics of that is the meaning of the different variables. So you have a magnetization M, which is a vector, and so it has x, y, z components, mx, my, and mz. The other thing you have is an effective magnetic field, H effective. So if you remember a few slides ago, we saw the off resonance condition where omega naught and omega is not equal and you have an effective magnetic field. That is what we are again talking about here. We have an effective magnetic field, which is the vectored addition of the z component and the xy component. And the z component is constant and the xy component depends on the magnitude of the radio frequency provided. In this, you can write, so you have a radio frequency provided. We have the amplitude h1 and frequency omega. E to the power I omega t can be broken up into sine and cos. And normally we write the x component as the cos component and the y component as the sine component. So these are the 6 variables in the Bloch equation. 3 variables are the mx, my, and mz. And the other 3 variables are hx, hy, and hz. Bloch equation is basically, these are equations relating how the different magnetizations are related to the different magnetic fields. When it is in terms of x, y, and z, it is the laboratory frame. Because x, y, and z are constant coordinates, that is, it is x, y, and z, it's a constant coordinate system. The direction of x, y, and z does not change whether your system is rotating or not rotating. So it's called the laboratory frame. And there are some other variables that we have already discussed in these equations, like gamma, the gyromagnetic ratio. We have T2, that is spin-spin relaxation, and T1, that is spin lattice relaxation. But this is not that much of use to us because it is talking about the laboratory frame. What is more useful to us is basically the rotating frame of reference. In that, what we do is we introduce 2 new vectors, u, which is in the direction of the radio frequency. So we were talking that there's a radio frequency field along the XY direction moving in the clockwise direction. We take the vector along this radio frequency field, and V vector we take 90° to the U vector. So it's called the orthogonal component. So using several mathematical transformations, we can transfer these XY equations to equations having U and V. And that is called the block equations in the rotating frame of reference. Again, the equation themselves are not useful for us. This is just for your knowledge. But what happens is that at equilibrium, and if you have a condition where there is no saturation. So we have already discussed that saturation, we call it when the upper and lower levels are equally populated. If you have a condition of no saturation, which is the normal condition that exists when taking NMR, and you have steady state, that is equilibrium conditions, then if you plot the U component, U vector, with frequency, you will get this kind of a signal, which is called a dispersive signal. And if you plot the V vector, that is perpendicular to the U vector, with respect to frequency, you will get this kind of a signal, which is called an absorptive signal. In NMR, the NMR instrument that is there, they are programmed in such a way that the dispersive signal is ignored and only the absorptive signal is kept in the spectra. So the resultant spectra that you observe, it will consist of many absorptive spectra, which is what you must have seen in the NMR spectra that you have. Now, so far we have mostly been talking about NMR instrumentation or the physics and everything, but now we'll look at the more practical aspects of NMR. So basically, if you imagine a nucleus, the nucleus is surrounded by a cloud of electrons. Now, when you apply an external magnetic field B0, this magnetic field will cause the electrons to spin. And here, I'll just this. In an applied magnetic field, the valence electrons of the protons are caused to circulate. This circulation is called a local diamagnetic current. So because of the magnetic field, the electrons are moving. And electrons are charged particle. Movement of charged particles is causing a current. And moving charged particles also generate a magnetic field in the opposite direction to the applied magnetic field. So if the applied magnetic field B0 is in the upwards direction, the induced magnetic field will oppose B0. I'm writing that as Bi. You can see Bi is in the downwards direction. This is called diamagnetic shielding or diamagnetic anisotropy. Basically, so if you have a nucleus, imagine you have an isolated nucleus without any electrons. The nucleus will observe full B0. But if you have electrons, then the field observed by the nucleus is actually B0 minus Bi. So the nucleus will observe a net field of B0, the applied field, minus Bi, the induced field. And this can be written, so here B has been written as H. It can be written as H0 1 minus sigma I, where sigma is the screening constant. So basically B0 minus Bi has been written as H0 1 minus sigma I. And so screening constant basically depends on the electron density surrounding the nucleus. If the electron density is high, so if you look at this diagram, electron density around the nucleus is high. So if there are more nucleus, the current generated by the movement of the, if there are more electrons surrounding the nucleus, the current generated by the movement of these electrons will be higher. So the induced magnetic field will be higher. So the effective magnetic field, I'll write this as B effective. B effective, that is B0 minus Bi, is lowered. So the nucleus is experiencing a weaker magnetic field. But if you have this situation where the electron density around the nucleus is low, if the electron density is low, then the induced magnetic field will also be low. And so B effective will be higher and the nucleus will experience a stronger magnetic field. So this kind of effect is called a shielding effect because the electrons are shielding the nucleus. And knowing the screening constant will give you an idea about the electron density surrounding the nucleus. So it will give you an idea about the structure of the molecule. Here, there is another concept called chemical shift. So instead of like magnetic fields or frequencies are things that can vary. So rather than that, a constant was defined by delta I called the chemical shift, which is defined as the HR minus HI divided by HR, where HR refers to a reference field and HI is the field in the nucleus under study. So if we are doing 1H NMR, HI is the field experienced by the 1H. And this is not that important. This one is more important. Where, so this equation can be transformed to this equation, where instead of the magnetic field, you have the frequency. So frequency, so the numerator is basically the frequency difference between your reference and the nucleus under study. So nucleus under study is, the reference normally something like TMS or tetramethylsilane is taken. And in the denominator, you have spectrometer frequency. And into 10 to the power 6 is done so that the units of delta I is parts per million or ppm. So this reference, why we choose TMS as reference, there are several points for that. Firstly, TMS is non-toxic. TMS is very inert, so it will not react with the compound that you are studying. There are other points also, but which you can go through later. So all these slides will be uploaded. The recording will also be uploaded and the slides will also be uploaded. So you can check that out and come back with your doubts later. But in TMS, so this is the structure of TMS, you have a silicon attached to 4 methyl groups. Because there are so many, so there are 4 into 3, 12 hydrogens. And all the hydrogens have equivalent environment. So because of this, only one signal is generated because all 12 hydrogens are equivalent. So it is a good reference, because if the reference only is giving multiple signals, it's not a good reference. Secondly, because it has 12 hydrogens, it produces a very intense peak. So small amount of TMS itself is enough. And silicon, so basically compared to silicon, carbon is more electronegative. So the electron density will be withdrawn towards the carbon. So these hydrogens will have high electron density around them. The nucleus of these 12 hydrogens will have high electron density surrounding them. So they will be highly shielded nucleus. And so the chemical shift will also be low. And so suppose this is the chemical shift of TMS. Your compound chemical shifts will generally come quite far from TMS. So there is no chance of mixing up your compound and TMS chemical shifts. So due to different reasons like this, TMS is one of the most commonly used reference compounds. Now, there are several factors that affect chemical shifts. Um, One is the electronegativity. So, suppose you have methane, that is CH4. There is no electronegative element connected to the carbon. So, you are studying the hydrogen attached to the carbon. And you have an electronegative element X attached to it. Now, as the electronegativity of X is increasing, X will withdraw more and more electron toward itself. So on the hydrogens, there will become a delta positive charge. Because of the delta positive charge on the hydrogen, the electron density surrounding hydrogen will reduce. If the electron density surrounding hydrogens reduce, this situation will happen where the net effective magnetic field experienced by the hydrogen nucleus is lower. And if the effective magnetic field experienced by the hydrogen nucleus is lower, then it will appear at higher values of chemical shift. It is said to be downfield shifted or de-shielded. So you can see that in the example, as you are going from fluorine to oxygen to chlorine to bromine to iodine, electronegativity is slowly will go in the opposite direction. So as we are going along this direction from methane, electronegativity of this X attached to the carbon is increasing from 2.5 to 4. As the electronegativity is increasing, electron density along the hydrogen is reducing. And because electron density along hydrogen is reducing, the chemical shift is increasing. You can see in methane it was only 0.3. The chemical shift delta increases to 4.26 in case of fluoromethane. Similarly, if instead of 1x, you have 2x, then there is even more withdrawal of electrons from the hydrogen and the delta positive charge will increase. So you can see as you are going from CH3Cl, where 1 chlorine is there, to CH2Cl2, 2 chlorine, and CHCl3, 3 chlorine. So as the number of the electronegative substituent is increasing, the chemical shift is also increasing in the same direction. So multiple substituents will have stronger effect than monosubstituted. Another factor is the hybridization. So when you go from sp3 to sp2 to sp, the S character increases from 25% to 33% to 50%. Now, as the S character increases, electronegativity also increases. So what we expect is that in case of alkane, there is a withdrawal of electrons. But in the case of alkyne, the withdrawal of electrons is much higher because this carbon is sp hybridized and greater the S character. So greater S character, greater electronegativity, and greater electronegativity, greater delta. This is what should have happened. But so when going from alkane to alkene, we see this delta increases. But this is a very anomalous effect that when going from alkene to alkyne, that is double bond to triple bond, delta should increase, but delta actually decreases. This happens due to another effect called the anisotropic or ring effect. So in ring effect, what happens is that if you imagine the benzene ring here, when an applied magnetic field is supplied along the upward direction, there is a ring current in benzene. Like here benzene is shown, but uh, if it is just a double bond like C double bond C or C double bond O, even then the pi electrons will form a current. And due to the current in the pi electrons, the magnetic field induced will be in the opposite direction in the middle of the ring, but it will be in the same direction outside the ring. So if you imagine the alkene molecule, you can see the double bond here, alkene. The induced magnetic field is shown by this dotted blue circle. So in this region, the induced magnetic field is opposing the applied magnetic field, which is in the upward direction. But in this direction, where the hydrogen is present, the induced magnetic field and the applied magnetic field are in the same direction. So this hydrogen is experiencing a much higher magnetic field than it should have experienced. And because it is experiencing this higher magnetic field, um, it is getting very much upfield shifted. Sorry, downfield shifted. So that is why on going from alkane to alkene, there is a big downfield shift. However, in case of alkyne, the situation is different. So alkyne molecules are linear. So here you have C triple bond C, and the applied magnetic field is in the upwards direction. Now, because of this applied magnetic field, there is a movement of the electrons in a kind of cylindrical motion. So you can see this cylinder shown here. The electrons are kind of spinning in this direction, and the applied magnetic field due to this is shown by these circles. So the hydrogen is here. Near the hydrogen, B0 is always in the upward direction, and near the hydrogen, this field is in the downward direction. So B induced is in the downward direction. So hydrogen, it is experiencing a much lower field because the induced magnetic field is in the downwards direction. Because it is experiencing this lower field, it is getting shielded. So in alkene and alkyne, the electronegativity effect is there, but much more important is this kind of ring effect, or also called as anisotropic effect, where there is due to motion of the pi electrons, there is a current that is forming, and due to that current, there is an induced magnetic field. Now, in case of alkene, what happens? B0 and Bi add up. So if you the alkene hydrogens are here. In case of alkene, the hydrogen is experiencing B0 plus Bi. We just saw here, because B0 is also in the upward direction and Bi is also in the upward direction. So in case of double bonded compounds like alkenes or benzenes, it experiences B0 plus Bi. So it is B shielded. But in case of alkyne triple bond, it is experiencing B0 minus Bi. It is experiencing a lowered magnetic field because B0 is in the upward direction and Bi near the hydrogen is in the downward direction. So it is experiencing a lower magnetic field, and so it is becoming shielded. That is why if we now look at the chemical shifts, this is explained by anisotropy. Anisotropy is basically this entire effect where due to movement of pi electrons, there's an induced magnetic field. So in alkynes, the magnetic field is B0 minus Bi. And because of that, it experiences a lower chemical shift. And in case of alkanes, it is B0 plus Bi. So it is experiencing a higher chemical shift. So if we had only considered electronegativity, we would not have been able to explain this phenomenon. But this phenomenon is a result of both electronegativity and anisotropy. And that is why alkynes represent a much lower chemical shift than expected. So we have mostly covered everything discussed in the first 5 lectures of week 1. So I'll just quickly go through the questions of assignment 0. Assignment 0 was just a practice assignment, so it was not marked anyway. So, but I'll just discuss the questions so you can know how to solve this kind of questions. So the first question was a very simple question that NMR uses which frequency? We have already discussed, it's the radio frequency. So basically, if you look at the electromagnetic spectra, if, you can see radio waves have is the shortest frequency. And gradually, as the frequency increases, you go to microwave, IR, UV, X-ray, gamma rays. This is the entire electromagnetic spectrum. Now, different spectroscopy uses different parts of this spectrum. So, NMR spectroscopy in particular uses only the radio waves. If you have IR spectroscopy, which involves molecular vibrations, then they use the IR or infrared part of the spectrum. If you have UV spectroscopy, it uses the UV part of the spectrum, and basically in UV spectroscopy, there is change in electronic energy levels. So as you increase the frequency, the energy of the electromagnetic radiation also increases because E is h nu. So frequency increase means energy increase. So as you go in this direction, the energy of the electromagnetic radiation increases. And in NMR, we know NMR is a very non-destructive method. That is, the sample that you use in NMR, it is not destroyed in any way, it is not affected in any way. This is because NMR uses radio waves, which has lowest frequency, that is lowest energy. So the radio waves used for NMR spectroscopy are very low in energy, so it does not harm the sample in any way. But as you gradually increase the energy, you tend to destroy the sample. Like suppose X-ray. In X-ray, what happens? X-ray crystallography, X-rays are supplied and the electron can be completely knocked out of the compound. So the compound becomes ionized. So the compound itself is undergoing a change, and it's called a destructive method of spectroscopy, or it's called ionizing radiation. But your NMR, which uses radio waves, it falls in the non-ionizing radiation. So the advantage of NMR is that not only is it very accurate and it is able to distinguish between the different types of hydrogens in different chemical environments, but it is also a non-destructive method because the energy of the radio waves are very less and they don't destroy the compound in any way. Next is that which of these nuclei don't have any magnetic moment, and this we have already discussed is 12 carbon, because we know the rule is that when both atomic and mass numbers are even, there is no magnetic moment and the compound is NMR inactive. In case of the first one, 1H1, both are odd, so it's NMR active. This is deuterium, where again mass number may be even, but atomic number is 1, so it's odd and it's NMR active. 15N, N atomic number is 7, again atomic number is odd, so it's active. But 12C, atomic number 6, where both are even, atomic number and mass number, it is NMR inactive and it has no magnetic moment. So if you just remember the basic rule, you'll be able to answer this. Then we have a small numerical where it is saying that a proton is in a magnetic field of 10 Tesla. And what is this in megahertz? So the simple formula is to remember is this. Frequency is gamma into B0, where frequency is in megahertz, gamma is the gyromagnetic ratio, and B0 is the magnetic field. Here we do not consider the negative term because we are just doing a scalar calculation of the magnitude. We are not considering direction. So we ignore the negative term. So here the question mentions proton. Proton gyromagnetic ratio is 42.58 and B0 mentioned is 10 Tesla. So if you replace that, then the Tesla will cancel out and you will get around 425.8 megahertz. And the option that is closest to this is 420 megahertz. So the correct answer is C. So you can just remember this formula and the gyromagnetic ratio of some of the common nuclei like 1H, 13C. Then you will be able to solve this kind of question. The next question is also a small numerical where it is saying that if the proton is absorbing an energy at 500 megahertz frequency, then approximately at what frequency nitrogen will absorb. So here the formula to remember, I'll come back to the option after this is solved. So here the formula to remember is delta E is gamma H bar B naught. And this is equal to H nu. So the delta E, that is the energy difference between the lower and upper states, is gamma H bar B naught, and we can also write it as H nu. Now, in the question, it has been mentioned that B0 is 500 megahertz. So this is constant. So B0 is constant and H is a constant. So if you divide this and this, so you have two equations for nitrogen and hydrogen. So if you divide them, the H bar and B naught will cancel out. So you will have nu nitrogen by nu hydrogen is gamma nitrogen by gamma hydrogen. So in this equation, if you take this equation for nitrogen and for hydrogen and you divide them, B0 is constant and H bar H are all constant, they'll cancel out. So you will get this relation. So gamma hydrogen and gamma nitrogen, as I said, so nitrogen, if nothing is mentioned, you consider this 15N, because 15N is the nitrogen that is used in spectroscopy. So nitrogen and hydrogen, if you use these two gamma values, you will get this equation that frequency of nitrogen is 0.1 into frequency of hydrogen. And frequency of hydrogen, it's already mentioned as 500 megahertz. So if you include that, you will get 50 megahertz as the frequency of nitrogen. And 50 megahertz is your option D. So basically, depending on the gyromagnetic ratio, it is the frequency of absorption changes. And if the gyromagnetic ratio, in this case, again, we are ignoring the negative sign because we are only working with, like we are just calculating the magnitude. We don't care about the frequency right now. We are not doing vector calculations. So we are ignoring this negative sign of the gamma. So if you can just remember this equation, you know that B0H will all cancel out. Then you can easily calculate the frequency like this. Another question is that which is the more sensitive nucleus? Now in this case, sensitivity of nucleus depends on two things. One is gyromagnetic ratio. Why gyromagnetic ratio is because there is this formula that the probability of transition P is 1/4 of gamma square into H1 square. So higher the gyromagnetic ratio gamma, higher is your P. And higher is your probability of transition, more sensitive is the nucleus. So higher gyromagnetic ratio means higher sensitivity. And secondly is the natural abundance. So suppose if you see the abundance of 1H and 2H. In nature, 99.985% of hydrogen is 1H. Only 0.015% is 2H. That is why we don't use 2H for NMR spectroscopy. Because suppose you have a sample, just a compound, so only 0.015% of hydrogen in that compound will be 2H. So the signal strength will be very low. That is why greater the natural abundance, I'm just writing it as A, greater natural abundance, greater is your sensitivity. Because more the abundance, more number of nuclei will be there and better will be your signal. In this case, some nuclei are given. And so if you compare these 4 nuclei, you will see that 31P, it has a natural abundance of 100%, meaning there are no isotopes. So because of this huge natural abundance, 31P is the most sensitive nuclei. So if you think of the others, nitrogen has isotopes. There is 15N, there is 14N. 14N is not shown here, but it does have that isotope. Carbon has 13C, it also has 12C. Deuterium is 2, so deuterium is 2H and 1H. All these three have isotopes. So the natural abundance is low. It is only 31P that has no isotope, and so the natural abundance is very high. And because of that, it is the most sensitive nucleus. This sir has already discussed in a video that how many peaks ethanol will have. Clearly, ethanol will have 3 peaks because there are 3 kinds of hydrogens in it. So the hydrogen that is directly attached to oxygen is most downfield shifted because oxygen is electronegative. So OH, most withdrawal of electrons and most delta plus. So OH is the most downfield shifted, then CH2 and CH3. So as the distance from O is increasing, the downfield shift or delta value is decreasing. So because there are 3 kinds of hydrogens, it will have 3 peaks, and the correct answer is C. Then this we have already discussed is that NMR spectrometer provides, basically we discussed that NMR is a non-destructive technique because it is a low energy radio frequency. So A and D are cancelled out, which are destructive. And we know NMR is very accurate. It can distinguish even between very small chemical environment differences of hydrogen. So it is option C, which is the correct answer. Then this is, I'm not sure why this was included in the assignment. This is just an equation of a straight line. So you know y equal to m. So equation of straight line, and so y equal to mx plus c. The equation given is 2y equal to 3x minus 6. If you just rearrange the equation so that you have it in this form, y equal to mx plus c, then your slope is 3 by 2 m and intercept is minus 3, that is C. So that is your option C, slope 3 by 2 and intercept minus 3. This is a general simple maths question, not a NMR related question. And there was one question which is just an information question, which was asking that what is used to cool the superconducting coil in NMR? So the correct answer is liquid helium. So this is actually the picture of an NMR spectrometer, and the sample is injected in a tube here. So basically, you need a very strong magnetic field for NMR, and to generate that strong magnetic field, you need superconducting magnets. And superconducting uh, condition can happen only when the temperature is very low. And liquid helium has a temperature of 4 Kelvin, which is one of the lowest known temperatures, which is why liquid helium is used in order to cool the magnet, which produces the B0 magnetic field. So your answer is B. And again, this is a basic question, is that the magnetic moment of the nucleus is related to what? So we have already seen that the nucleus is a spinning charged particle, and any spinning charged particle will have an angular momentum I, and because it is a spinning charged particle, it will behave like a tiny magnet. So the magnetic moment is generated by the spinning of this charged particle, that is the angular momentum. So magnetic moment is related to the angular momentum, not to any of the other options. So I've covered a lot in this discussion. As I said before, I'll share all the slides and the recording also, and you can go through it, and you can come back with all your doubts in the next class. That will be next Monday. So I'll stop the recording now.